This video, I'm going to be going through the problems in homework 1 for Achieve. Question number 1 is asking you to rank these 3 radicals in order of stability, putting the most stable up at top and the least stable down at the bottom. As a reminder, the methyl radical is the least stable out of all of the radicals. We want to have alkyl groups or R groups attached to that carbon, donating electron density in to help stabilize that radical. The most stable radicals are the benzylic and the allylic radicals. And then from there our tertiaries, and then our secondaries, and then our primaries. Tertiary being a radical that has a single electron on a carbon atom that is attached to 3 additional carbon atoms. A secondary would have only 2 additional carbon atoms, and a primary would have only 1. So these would be hydrogens. Question number 2 is similar. It's asking you to classify each of these as primary, secondary, or tertiary. Whether we're talking about radicals or carbocations or whatever, a primary radical is going to be one that has the unpaired electron on a carbon that is attached to only one other carbon. The other bonds are to hydrogens. Secondary radical has 2 additional carbons attached. And then a tertiary radical is one that has 3 additional carbons attached, no hydrogens on that carbon with the unpaired electron. Question number 3 is asking you, is giving you a set of reactions. There's more than what I'm showing here, or steps in reactions. And it's asking you to classify them as initiation, propagation, or termination. An initiation step is one where you have 2 radicals that are reacting together. I'm saying that backwards. An initiation step is when you have a non-radical and it turns into 2 radicals. So to classify these initiations, what you're going to be doing, like for example right here, you're going to be looking at the reactants, that's a non-radical, looking at the products, there's 2 radicals, so that would be an initiation. A propagation is where you are taking a radical and you are turning it into a different radical. And there could be more than one, like 2 radicals turning into 1 new radical, or 1 turning into 2, or whatever. But you're starting with a radical and ending with a radical. And then termination is the opposite of initiation. This is where we have 2 radicals and you are turning that into a non-radical, ending with none. So for all of these, you're just going to be looking at each one of these reactions and you're just going to be asking yourselves, do I have radicals on the left? Do I have radicals on the right? And then fitting them into these boxes. Question number 4. You are being given a mechanism and you're asked to draw the product. So notice that these are half arrowheads or fish hook arrows. These each indicate the movement of just 1 electron. So for each of these arrows that we're looking at a movement of a total of 3 electrons. We've got 2 arrows coming out of this bond right here, which means that both of the electrons, the 2 electrons in this bond, are being moved. That would mean that this bond is breaking. It's not going to exist anymore. So I'm gonna draw the 2 electrons in this bond as dots, and I'm going to draw these electrons as dots as well. So for this product of this reaction, we're going to take these 2 electrons. One of those electrons is going to get moved onto that carbon atom. That's going to be a radical. And then the other electron in that bond, it looks like it's being moved over to this bond right here. And I get some color coding going on here. As a result, this bond is just going to completely break because those electrons have been moved. Now, what do we have going on with this curved arrow? It looks like in that situation, we're taking, that curved arrow is starting at this electron. You know, I need to move this out of the way so we can see the arrow. So this third curved arrow is starting at this electron, and where is it going? That electron is being moved into this bond right here. So that means we're going to be making a double bond in this spot. And then, yes, this unpaired electron, that needs to go away because we moved it into this spot. So it looks like we're going to be ending with 2 things over here. We've got this molecule that we're making, and then we've got this molecule that we're making as well. You're gonna have two different molecules in that box. And question number 5 is really similar. The only difference, I guess, with this is that this question was in condensed notation and this one is in line notation. But if it's helpful, you can draw those dots in. It looks like we're moving this electron and then we're moving these 2 electrons as well, and just relocate those electrons and see what you end up getting. Not necessarily going to get 2 products over here. Probably not, because it says it's a resonance structure. I didn't catch that at first. So there's only going to be 1 molecule that you're going to draw in this box, and it's going to be a resonance structure of this guy. Question number 6 is pretty long. I'm not showing the whole entire question here on this slide. It's a series of propagation steps. Well, actually, they're not all propagations. It's really just these 2 right here. And there's more stuff down here, but these are the only 2 parts that you have to actually do something with. It's describing this reaction right here. So this guy up here is the overall reaction. And then in this spot right here, you've got arrows. You've got 2 curved arrows, and then 2 fishhook arrows. And what you have to do is drag the arrows into these boxes. These are pointing like this. So you want to be really careful when you're choosing the right arrows to drag. Pay attention to whether it's a full arrow or a half arrow. You want to make sure that you're picking the correct one. And what you're going to be doing, you really don't need to focus on the overall reaction right here. You really just need to focus on the steps that you can see. So for filling in these 3 curved arrows, it's propagation. So we need 3 curved arrows. Because it's propagation, we know that they need to be the radical arrows, the single arrowhead or half arrowhead arrows. And we want to look ahead to the product of that reaction to help us figure out what arrows go into these boxes. So when we're looking ahead here, we can see that the this carbon-hydrogen bond ends up breaking because it's not there anymore. So that means that we are going to need to have 2 arrows coming out of this bond showing both of those electrons breaking. Where do those electrons go? Well, we can see that one of them is ending up as a radical on this carbon atom. So we know that we need to have 1 arrow going this way from the bond. But what about the hydrogen? Where does the hydrogen end up going? It's kind of sneaky the way that they've put it into this problem. Notice down here that they wrote minus HBr. That's really weird notation. And this is just another way of writing that HBr is produced by the reaction. So it's just saying, hey, HBr is being taken away from this molecule. So that's where this hydrogen is going. This hydrogen is combining with this bromine radical to make an HBr molecule. And you need to be making that HBr bond because it doesn't already exist. It's kind of hard to see it because the unpaired electron is lining perfectly up with their little box here, but there is an unpaired electron on this bromine that you can use to make that HBr bond. And then for this box, you're going to do the same thing, although to help you figure out the curved arrows that go into these boxes, you need to look at whatever is drawn down here, which I don't have that part on this slide. But when you look at the problem, when you see the whole entire thing, you need to look at what is at the end of this reaction arrow. What is this molecule being turned into? And what bonds need to be made and what bonds need to be broken, and that should help you fill that in as well. For question number 7, this is telling you that you have propane and you're reacting it with the chlorine in a radical reaction. And it says that if you trichlorinate, so that means you would be adding 3 chlorines to the propane molecule to give you something that has a formula that looks like this, C3H5Cl3. There are going to be 5 different isomers, 5 different isomers that have the molecular formula C3H5Cl3, and you've got to come up with all 5 of those. Now, there are, as far as I know, there's 2 ways to do a problem like this, and one of them is just to go at it and just start drawing as many isomers as you can come up with. But you can also do it somewhat methodically, like kind of strategically. So all of these are going to be propanes, and we know that there's 5 of them. So I can start by just drawing 5 propane carbon skeletons, because I know that I'm going to need to have all 5 of those. And then I also know that I'm going to be putting 3 chlorines on each one of these molecules. So I could start, one option would be to put all the chlorines on carbon number 1. And that would be exactly the same as putting all of the chlorines on carbon number 3. So I don't want to do that. But what I'm going to do next is I want to be methodical about this. So what I'm going to do next is say, what if I were to take one of these chlorines and move it over to carbon number 2? And then what if I were to take, that's a different molecule. What if I were to take one of the chlorines and move it over to carbon number 3? That would be a different molecule. And that would be all of the options that I have for just moving one carbon. So now what if let's go back to that. What if I take the second carbon or second chlorine and I move it also onto carbon number 2? Twist this a little bit like that. Or what if I were to move it onto carbon number 3? And just kind of, approach it like that. Go through all of the different possible places that you could fit 3 chlorines. Keep in mind that you're not going to be fitting 3 chlorines onto carbon number 2, because that would give that carbon atom 5 bonds. That's way too many. So don't try to jam 3 chlorines on the center carbon, but you should be able to come up with all these structures. This is a really similar question. This is saying that you have a pentane molecule, so that's going to be a 5 carbon chain, 1, 2, 3, 4, 5. And it says when it's monochlorinated, you get 5 different isomers, C5H11Cl. And it's asking you, was the gas N-pentane, isopentane, neopentane, or a mixture of them? So first thing, you're going to need to know what all of these different isomers are. This is N-pentane. The little N stands for normal, meaning just normal pentane. Isopentane is what IUPAC would call 2-methylbutane. And neopentane is going to be this guy right here, what we would call 2,2-dimethylpropane. And it wants to know if you're monochlorinating, you're going to end up with 5 total molecules. The way that I would solve this problem is I would just I'm just going to kind of move these 2 out of my brain. I would monochlorinate N-pentane first, and I would ask myself, if I'm going to do chlorination of this guy, how many isomers can I make? And we're only thinking about constitutional isomers. We're not thinking about stereochemistry at all. So how many isomers can I make from this guy? Maybe, let's just say maybe it's 5. And if it is 5, then that's going to be the answer to the question. But spoiler alert, it's not 5. It's going to be some number less than 5. So we've got that. We're going to kind of move that out of the way. And now I'm going to do the same thing over here. I'm going to imagine, what if I chlorinated this guy? And I want to know, again, how many isomers can I make? How many different isomers can I make when I chlorinate that guy? Kind of set that aside. And then I'm going to do the same thing with this one. How many isomers can I make? Now we know that it's telling us that the product had a total of 5 isomers. So what we want to do is come up with, how many of these do I put together to make 5 isomers? Let's just make up some random numbers. Let's say that this guy made 6 isomers. It did not, but let's just say that it did. Let's say that this one made 3 and this one made 2, and I know that my mixture had a total of 5 isomers. So with that information, I could say it's definitely not this, because if I had this guy, I would end up with 6 isomers, and I've only ended up with 5. So I can rule this guy out. Also, it's not this one, because this would only give me 3 and I have 5. And it's not this one, because it only gives me 2 and I have 5. But 3 plus 2 equals 5, which means that I must have started with a mixture of both of these. And when they were chlorinated, their isomers add up to a total of 5. Over here, it's asking you to draw the major monobromination product. So looking at what you know about the bromination reaction, heat is an initiator for the bromination radical reaction. So all you have to do is just put the bromine in the correct spot. It's pre-drawn. All that you're doing is adding a bromine. That's all you have to do. Put it in the right spot. For this one, more like the couple of ones that we were just doing, this is saying a chlorination of alkanes. Chlorination gives you a mixture of products. How many monochlorinated and dichlorinated products can you make if you're starting with 3-methylpentane, considering constitutional isomers only? So again, what we're going to do, let's just kind of start with the monochlorinated. We want to think of every possible place that we could put a chlorine on this molecule, every possible carbon, and also keeping in mind that some locations are identical. So if we put a chlorine here versus if we put a chlorine here, we're making the exact same molecule. So we wouldn't count that as two different structures. Here versus here, it's all the same thing. Here versus here, also just one molecule. And then we want to do the same thing for dichlorination. So we want to consider all of the possible places, unique places that we could put 2 chlorines on this molecule that would give us a unique product. For this one, this is asking to draw the expected major products. There might be more than one. There's 2 parts to this, a part A and a part B. When we're chlorinating, remember when we're chlorinating, chlorines go everywhere. They're not selective. So we want to draw multiple products whenever we're chlorinating. One thing I want to warn you is that you still are not allowed to touch the carbons of a benzene ring. We haven't learned any reactions that do that. So ignore those carbons. They're not available to you yet. You're not ready for those. You only have 2 carbons available to you in this reaction. For this next one, we have NBS. Remember that NBS is just a source of the bromine radical. And so NBS, bromine, is selective, meaning that you're only going to have one product of this reaction. And still, no touching the carbons of a benzene ring. So you've got 4 carbons to choose from, and you need to choose the one best carbon for the bromine. This is weird the way that this problem is written. This one, I have to see what the question is asking. This one is asking to draw the structure of the major product. And this is laid out funny. So N-bromosuccinimide is NBS. Remember, that is the source of the bromide radical. The peroxides, that's the initiator for the reaction, like light or heat. And CCl4 is the solvent. So we can ignore this information. It's not giving us anything useful. And this is our reactant. So maybe we'll put it on the arrow to make it look a little bit more normal. And you just want to draw the one product of this reaction, because remember that bromination is selective, meaning that the bromine is going to go onto the one best carbon. Don't touch the carbons of the benzene ring. You're not allowed to touch them yet. And here, this problem is a bit of a doozy. So this has your starting molecule, and it has NBS, which is your source of bromine, and then it has your initiators, as light or heat. And then it has all these possible products, A through G, and it wants you to pick, it gives you an option to pick as many as you want. Products, which are the products of this reaction. So this problem is actually really tricky because you need to take into consideration the resonance structures that could be formed after the radical is formed, but before the bromine is added to the molecule. So, sometimes it's easy to forget the mechanism of the reaction. The first thing that happens in this reaction is abstracting a hydrogen and forming the radical. That's going to be the first thing that happens. So in this case, it's most likely going to be abstracting that juicy allylic hydrogen right there. And that means that we're going to be making this radical. This is what the radical is going to look like. This is the molecule that's going to get brominated. So some of our product is, I'm just kind of giving it away. Some of our product is going to be this guy, showing that bromine going right onto that spot. But this radical, this allylic radical, is so stable because it has resonance. You can take that double bond and you can draw a resonance structure with that double bond. So you need to consider the resonance structure for this molecule and then consider the bromination of the resonance structure as well. Next, we have another NBS bromination. So down here, this N-bromosuccinimide, this is NBS. It's telling you up here AIBN azo-bis isobutyronitriol. This is an initiator. So this is just like peroxides or like heat. We don't need to pay attention to that. That's just going to distract us. We're just going to be drawing the structure of the one product bromination of this molecule right here. And then over here, next, question number 15, we have an anti-Markovnikov addition of HBr. So this is actually just kind of a throwback to the alkene addition reactions that we did last quarter. HBr in the presence of peroxide. This means that you are adding an H and also a Br to the carbon-carbon double bond. Anti-Markovnikov, no rearrangement. Draw the major product for that reaction. This one, two-step reaction. I'm going to be using some of the stuff that you learned from this quarter, this chapter, and then also some stuff you learned from last quarter. You're going to start by drawing the product of brominating this guy right here. Draw that in this box. That's going to be an alkyl halide. And then you're going to react that with our friend tert butoxide. There's some distractors here. Ignore this down here is the solvent. You can also ignore our spectator cation. Take a look at what we have. That's our friend tert butoxide. That is our, what we call our bulky base. So for this, you're going to need to think back to 241 when we were doing reactions with the bulky base. And then the last three questions that you have are multi-step synthesis questions. There's more in this box than what I'm just showing right here. I think that the hints that I'm going to give you for this, I think that what you should do is start by filling in your reactant and your product, and then just kind of work from there. Now, one of the things that's kind of tricky about these is that it is using nomenclature that we haven't learned yet, but you have the internet available to you to help you with all this kind of stuff. So you can just look up ethyl benzene. You can just type it. We're not going to learn 100% of all the nomenclature in general. So, you know, this is what people do when they can't figure out the name of a molecule. Here's our ethyl benzene molecule. It's a benzene ring with an ethyl group attached to it. So what you're going to do is, looks like ethyl benzene is right here, but you're just going to start by filling this guy in, your ethyl benzene, and then fill your product in as well. That should be the second thing that you do. So you can get a good visual of what kind of transformation you need to make. This guy down here is 2-bromoethyl benzene. Let's see what the internet tells us about that. 2-bromoethyl benzene. And there it is, right there. So that is going to be this guy, like that. And then for each of these, you are filling in your reagent and then an intermediate, and then your next reagent and your next intermediate. So it looks like this is a 3-step reaction. Now, this at least makes it a little easier to visualize. Remember all of the things that you've already learned. For example, do we need to make any changes to the carbon skeleton? That should be the first thing that we're looking at. Looks like we're not making any changes to the carbon skeleton. We're just putting a bromine on the molecule. And it looks like it's just going to take us a couple of steps to get the bromine exactly where we want it. So the first thing that I'm seeing when I look at this reaction is that I'm starting with a molecule that has no functionality. It doesn't have any functional groups on it at all. It doesn't have any leading groups. It doesn't have any double bonds, because remember, you're not allowed to touch these carbons. They don't count. So this is, you know, all that we're looking at here, just this much of it. There's nothing going on here. And in that case, the very first thing that we should do is halogenate. I don't know because I can't see all of the options in the answer bank. I know that there are more things down here, but we need to halogenate to start with. So maybe it's going to be something like a Br2 with light. Like I said, I don't know what the options are down here, but we need to start by halogenating. And then in this box, you're going to draw the product, or you're going to choose the product of that halogenation. So if we were to halogenate this molecule with a beautiful benzylic carbon, where would that halogen go? It's not going to go where we want it to. It's going to go on the other carbon. So it's going to go right here. And now our job is to move that halogen out to the outer carbon. And we've done problems like this last quarter. If we want to move that halogen out to the outer carbon, we have to begin by taking it away. So in this step, we're going to do some sort of elimination. We need to eliminate, I don't think that's how it's spelled, eliminate, which means that we're going to end up making an alkene here. This is going to be an alkene. And then what we're going to do is put that bromine back. And when we put it back, this is going to be an addition reaction, not going to be a halogenation reaction. It's going to be an addition reaction, putting it back in the spot where we want it. Both of these steps are going to be things that you learned in 241. So you're going to want to look back in your notes or dig back into your brain. Then for the rest of the questions on here, I guess it's 4 of them, it's the exact same type of thing. Start by finding the structure of your reactant and your product. Take a look at how many carbon atoms you have. Do you need to make any changes to the carbon skeleton? If you don't have functionality to begin with, then start by adding your functionality. Put a halogen on there, put a bromine on there. And that's going to be the same for all of these. You are going to probably, not this one, but you're probably going to need to Google some of the structures for these molecules. And look them up. Don't be stressed about that. But you can totally do these. Just make sure you're giving yourself enough time to solve these problems because these ones are pretty tricky.